We've solved the Levinson-Durbin recursion algorithm for a specific right-hand side, and now we need to move to a general right-hand side. It's really the tricky part is the matrix that we would normally have to invert, and we're trying to avoid inverting that matrix. So our solution is going to be different. So instead of the z and the beta in that first vector for which we were trying to solve, we're going to call this w and alpha. And we're going to call this whole vector here that we've subdivided into w and alpha, we're going to call that x. Okay, we're going to proceed in much the same way, but it turns out because we have this general right-hand side, we're going to have just a few more steps. I should note that I know you've already watched almost a half hour of lecture on the Levinson-Durbin algorithm, and we don't even have the general solution yet. But this part should be a lot quicker. We have all the tools in place. We have the general recursion ready to go. We just have to deal with the fact that we now have this general right-hand side instead of an h. Okay, let's proceed as we did before. We'll use that equation to solve for w. And as before, we're just going to assume we have h inverse n minus 1. That will be times, whereas before we had our h, we now have our y n minus 1 minus alpha j h n minus 1. Okay. Once again, we're going to assume that we know the solution to the smaller problem. X n minus 1 is equal to h inverse n minus 1. And just as a recollection, I guess I should put this up here. This is h of n. And this is our vector y of n. So we're going to assume that we have the solution to the smaller problem. X of n minus 1 is equal to h n minus 1 inverse times y of n minus 1. And we're also going to assume that we know v n minus 1 is equal to h inverse n minus 1 times h n minus 1. So that came from our previous case where we had the specific right-hand side. If we know those, then we can rewrite our expression for w as w is equal to x n minus 1 from those first two terms. And following the same logic that we did last time, we're going to get alpha j, and then we have h inverse n minus 1 times little h of n minus 1. And that's going to give us, as before, our v n minus 1. So that comes in handy there. From these, we get the alpha is equal to y n minus h n minus 1 transpose j x n minus 1. all over h0 minus. This should all look somewhat familiar at this point. So given the solutions to both of those smaller problems, like we did last time. Last time we just needed the solution to one smaller problem. Now we have the solution to two smaller problems. We can compute the solution to the next size up. Specifically, from the equations up above, we would have x of n is equal to w, and I'm going to put n minus 1 in here so we can keep track of things. N minus 1 alpha, and our w, n minus 1, is going to come from our x, n minus 1, minus alpha j v, n minus 1. We get alpha there. And so this term we have is the solution to that one. This term we have as the solution to this problem. And alpha we have computed up above. And so solving the general case involves solving that specific right-hand side and then using one extra step to come up with the solution for the general right-hand side.